We conducted an ecologic study using existing data from the Peruvian Ministry of Health and the Pan American Health Organization to look at the possible association between the prevalence of leishmaniasis and distinct levels of relative and extreme poverty as defined by the World Bank. Based on known risk factors for the disease, we tested the hypothesis that people who live in conditions of extreme poverty, who are trying to survive from day to day and live in dwellings with little or no protection from the elements, would suffer higher rates of leishmaniasis than people living in conditions considered substandard or below adequate standards of living. No one, to our knowledge, has studied the association between leishmaniasis and two levels of poverty before. We additionally controlled for 3 different types of geography found in Peru that could potentially affect vector distribution. Leishmaniasis is a parasitic disease that is spread by the female sandfly. Like mosquitoes, the sandfly is able to infect people while taking a blood meal. The greater the chances of being bitten, the higher the chances of contracting leishmaniasis. Although the fly is capable of living almost everywhere, its distribution may be affected by elevation and terrain. We thus stratified our data according to 3 known predominant geographic types of areas. We focused our study on cutaneous leishmaniasis, the most common form of the disease in Peru and in most of South and Central America. The disease can cause skin lesions, ulcers, and severe disfigurement, leading to social implications for both children and adults, and, if left untreated, can affect productivity and cause poor performance in school by children. It can also lead to other infections causing greater illness. Known risk factors that support our hypothesis include exposure to tropical rainforest land that has been cleared and cultivated with crops such as coffee and cacao. This includes working or living in or close to such areas. Birds kept inside the home, especially chickens, or the absence of dogs and cats around the home. And most importantly, low socioeconomic status. Poverty is often associated with less education and a lack of literacy, non-durable wall materials in homes, and the absence of gas stoves to cook on, and usually the need for outdoor cooking. Poverty also brings challenges with malnutrition, sanitation, people living in close proximity to infected individuals, lack of knowledge about the disease, and lack of access to medical care. If we can show an association between leishmaniasis and specific populations, such as those living in relative or extreme poverty, then prevention and treatment interventions can be targeted where they are most needed.
The next section of the discussion focuses on part 1 of our methodology, that is geospatial analyses. Geospatial analyses is a technique used widely in public health and other disciplines to depict data on maps. You've heard that a picture is worth 1,000 words. Well, we would argue that so is a map. We use geographical information systems, or GIS as it's commonly referred to, as the tool to create the maps depicting leishmaniasis prevalence rates by relative and extreme poverty level percentages, respectively. Before creating the maps, we had to determine the degree of spatial relationship between the neighboring regions. In order to accomplish this, we applied the Moran's eye statistic to compare the data from neighboring regions in order to determine the degree to which geographic units, and in this case would be regions, were spatially dependent or spatially independent of each other. Based on the Moran's eye statistic results, z-scores and p-values for comparisons between Peru regions, leishmaniasis rates, and relative and extreme poverty percentages, we concluded that the regions did not differ significantly from random. Therefore, there was spatial independence across the regions. You can readily see the prevalence of leishmaniasis as well as the percentage of relative and extreme poverty for each region on these 2 thematic maps. The prevalence rates for leishmaniasis are represented by purple proportional symbols or circles that you see on the maps. The symbology is proportional to data values, therefore the size of the symbol for leishmaniasis prevalence is proportional to the rate data value. Thematic maps were used to display spatial distribution of the attributes relative and extreme poverty, and to also show the thematic connection of the geographic regions. The relative and extreme poverty level percentages are represented by color-coded polygons on the thematic maps that range in color intensity from yellow to red on the color spectrum, yellow being the lower poverty percentages and red being the higher poverty percentages. Depiction of leishmaniasis prevalence rate indicate that the highest leishmaniasis prevalence rate was for Cusco, which was 91.7 per 100,000 population, while the lowest rate was for Apamurak, which was 2.7 per 100,000 population. The highest leishmaniasis prevalence rate was 67.6 per 100,000 population based on the highest percentage of relative poverty, which was 34.8% for Amazonas, while the lowest leishmaniasis prevalence rate was 4.0 per 100,000 population based on the lowest percent of relative poverty, which was 14.6% for Lima. The highest leishmaniasis prevalence rate was 31.9 per 100,000 population based on the highest percent of extreme poverty, which was 27.3% in Loreto, while the lowest leishmaniasis prevalence rate was 4.0 per 100,000 population based on the lowest percent of extreme poverty, which was 0.8% for Lima. Now, GIS is a very useful tool in that we can see the data visually, but we use statistical techniques to evaluate our data further, and that was our next step.
Coming to methods, 25 regions of Peru were chosen as the units of observation for this study because they coincided with the smallest geographical area for which leishmaniasis case data were reported, which were available for only 18 of these regions. The regions were classified into 3 geographic types: coastal, mountainous, or jungle, according to the predominant geographical characteristic and based on the location of the majority of the population. The rates of leishmaniasis per 100,000 population was the dependent variable, and percentage extreme poverty and percentage relative poverty were the 2 independent variables of interest. The relationship between these 2 variables was studied by linear regression analysis using Stata12 and scatter plots. Since one region was a considerable outlier, robust linear regression was employed to treat the influential variables from this region. The figures here show the relationship between prevalence of leishmaniasis and percentage relative poverty by geographic type. The scatter plot on the left shows that one jungle region, Madre de Dios, was an outlier, which when excluded considerably changed the relationship, that is reversed it, as seen on the right hand side. The data outputs for both the ordinary least squares and robust linear regression models are shown in the table here. Model 1 is the ordinary least square regression and model 2 is the robust linear regression. So it can be seen that the p-values are not significant for any of the pairs. Similar relationships were obtained for extreme poverty and leishmaniasis rates, and it was not found to be significant. So it was concluded that there was no significant association between the 2 levels of poverty and the disease rates for both the overall regions of Peru and either of the 3 geographic types.
Analysis showed no statistically significant association between leishmaniasis prevalence rates and either relative or extreme poverty percentages. Lack of statistical significance could be due to limitations of this study rather than a true lack of an association between the variables. 7 of the Peruvian regions were missing leishmaniasis prevalence for 2009. Therefore, only 18 regions could be included in the analysis. Also, geographical regions were not homogeneous for coastal, jungle, or mountain. Some regions had a mixture of geography types which could influence the prevalence of leishmaniasis within the region. It is also possible that controlling for geography type did not properly control for vector density as we had hoped. Lastly, we were unable to control for population proximity and exposure to areas of deforestation which are known factors of leishmaniasis. Our recommendations for future studies include the following. Improved surveillance. At this time, leishmaniasis prevalence is likely underreported. Therefore, true impact of the disease will not be known until we have more accurate data. We should also acquire and incorporate data on deforestation, climate change, and vector density into further studies. Previous studies link such variables to disease prevalence, and by obtaining this data, we can more accurately identify who in the population is susceptible to leishmaniasis. As in any health campaign, education is vital. We must educate communities and health professionals how to recognize early symptoms of leishmaniasis and how to reduce one's risk of getting the disease through personal prevention measures such as wearing long sleeves and pants and avoiding being outside at dusk when the sandfly is most active. If you would like to know more about this project, please check out the paper by Cazort, Kale, Lupto, and Venuto entitled Ecologic Study of the Association Between Poverty Level and Regional Leishmaniasis Prevalence in Peru.